All right, so this is lesson 2.4b, limits at infinity and horizontal asymptotes. The idea here is we would like to find the limit of x cubed as x approaches negative infinity and as it approaches infinity. Mathematically speaking, we're just asking for the in behaviors of the function. When you look at the actual function here, you will notice that if I go forever to the left, right, so this way, that my function goes down forever. And then if I go forever to the right, my function goes up forever. So in understanding these behaviors, it's easy to just make the decision that the limit of x cubed as x approaches negative infinity is in fact negative infinity towards the left, and that the limit of x cubed as x approaches positive infinity is infinity to the right. And one thing we note in a pre-calculus class is that the in behavior is highly dependent on the even or odd nature of the function. That is, if a function has an odd degree, that one end goes down and one end goes up. And if that odd degreed function has a positive coefficient, as in this case, a 1, we know that the end towards the right goes up and that the end towards the left goes down. Versus if I had, say, negative x cubed, it would be reversed, right? So the right end would go down and the left end goes up. Whereas if a function is even, so for example, let's say we had an x squared or x to the fourth, we know that both sides of the function go up, whereas if I made them negative, we would notice that both sides of the function would go down. And so oftentimes it's enough to just note that the degree of the function tells us about the ends. All right, let's take a look at example 2. So the limit of x squared minus x as x approaches infinity. We note here that the highest degree is 2, meaning this function will end and begin the same way. Because there's no coefficient, it's a 1, so it's positive coefficient. So we know that our function here will end in both directions up at positive infinity. So when we approach infinity, we know this goes to infinity. And we see that in the graph. Now here, we have the limit of x squared plus x over 3 minus x as x approaches infinity. Now, with this type of problem, we're going to have to tackle it a little bit differently. We cannot plug in infinity because it's not a value. And we don't really know what this looks like as is. So what we're going to do is we're going to take this function and we are going to divide everything by x. Just like so. And we note that this can be rewritten as the limit as x approaches infinity of x plus 1 over 3 over x minus 1. Using the rules we learned before, we know anytime I have a constant over x and we approach infinity, we get 0. So we know that this is mathematically equivalent to the limit as x approaches infinity of x plus 1 over negative 1. That is, this is the limit as x approaches infinity of negative x plus 1. Now we note here that the graph of negative x plus 1 looks something like this, and that if we approach negative infinity, we'll notice, or approach infinity, we will notice that our function goes down to negative infinity. And if we look at the actual graph, we can see that. All right, last one. Sketch the graph of f of x equals x minus 2 squared times x plus 3 by finding its intercepts and its limits as we approach negative and positive infinity. Let's start with the intercepts, because that's a very pre-calculus skill. We'll start with the x-intercept. The x-intercept is found when y is equal to 0. So we will take this function, f of x, which is y, and we will set it to equal 0. So x minus 2 squared times x plus 3, and we will set the function equal to 0. Using the zero product property, we know that means x minus 2 squared equals 0, or x plus 3 equals 0. We know that means x minus 2 equals 0, or x equals negative 3, or x is equal to 2. So we see that we have intercepts at 2, 0, and at negative 3, 0. Now we can find our y-intercepts. And we know that y-intercepts are found by looking at x equals 0. So we'll plug in 0. F of 0 is 0 minus 2 squared, 0 plus 3. 0 minus 2 is negative 2. Negative 2 squared is 4 times 3, so 12. So we have a y-intercept at 0, 12. Lastly, let's go ahead and let's find our in behaviors. So we have the limit as x approaches negative infinity of our x minus 2 squared and x plus 3. Now note, we're going to use the limit laws to assess this. If we look at the first piece, this x minus 2 squared, we know that that's a quadratic. And we know that a quadratic that has an even degree, that both ends go up or both ends go down. Because there's no negative coefficient in front of the x, or this expression, we know that both ends go up. So if we go to negative infinity, we know that this piece of the function goes to infinity because both ends go up. Now the second function here, this one is a linear function. And we know that a linear function towards the left, if this is a positive slope, will go down to negative infinity. So infinity times negative infinity is negative infinity. So we know that the behavior of our function is towards the left going down to forever. Now we'll check the other direction. The limit as x approaches positive infinity of x minus 2 squared times x plus 3. Same idea. The first function is a quadratic. So quadratics, both ends up or both ends down because it's positive, both ends up. And then x plus 3 is a linear function. So to the right, it goes to positive infinity. Infinity times infinity is infinity. So we know now that both of our functions go up. Both ends go up. So let's make a sketch. We have an intercept at 2, 0. We have an intercept at negative 3, 0. And then we have an y-intercept at 12. We know that our ends to the right go up and our end to the left goes down. So we'll start with those. And then we know that our function goes through negative 3. And then we know that at 2, we have an x-intercept, but we know that this x-intercept occurs twice. And we call that in math a double root. And a double root creates a bounce. So we know it's going to bounce at 2 and come back up. And that's all.